Okay, we have here another integral from MIT 2022. We've got the integral from 0 to 2 pi, 1 minus cosine x all to the fifth, cosine of 5x dx. Okay, at first I was really dreading this one because when you multiply this out, you get like 6 terms, and then you've got all different powers. So multiple terms, power reduction, it seems really tedious. So instead of just grinding through the process of reducing the power on multiple terms, I want to see if we can get some shortcuts. And I think the whole key to this is going to be these two formulas over here to the right. We want the values of n, a, and b to be all integers, and we want a not equal to b. Now the n part's no problem. The n part's just going to be 2, because we know what that is, because we've got 2 pi as our upper bound, we've got 0 as our lower bound. Now this first one should be pretty clear, because when you integrate cosine, you're going to get something with a sign in it. If you evaluate sine at 0 or an integer value of pi, it's always going to be 0. So this is going to be the way we can kind of zero out a whole bunch of different integrals. And then for this second one, it's just kind of one step removed from this one. So when you've got cosine of different angles, a and b, we want a not equal to b, then you can reduce it with this formula here. And then what's going to happen is, don't worry about the constant, you're going to get a cosine integral, you're going to get another cosine integral. When we integrate these, we'll just use this formula, we'll get another sine, and that's going to be 0. So the idea of this strategy here is that if you expand this out, we're going to get a lot of integrals in either this form or this form, and then we'll just cross them off and call them 0 so that we can just focus on anything that's not 0. A couple other things we can use for this is our cosine cubed formula. What I'm going to try to do on all this is reduce everything to a single power, so we don't want any cosine squareds, cosine cubes, we just want everything to be cosine, but different angles are okay because we've got this tool over here that's going to allow us to zero those out. And you're probably familiar with the formula to reduce cosine squared, but one other thing I'm going to want is I want a formula for cosine to the fourth x. To get a formula for cosine to the fourth x, I can just take our formula for cosine squared and square it. Then this is going to be cosine to the fourth, and then we'll square the right side. But then on cosine squared 2x, I can just use this formula again with the angle being 2x, and putting in there, that'll become a 4x. So this part right here is going to become 1/2 1 plus cosine 4x. Then we'll just clean it up. I'll keep the 1/4 in front, so we're going to have 1 plus 2 cosine 2x. We'll distribute the half in, so this is going to become 1/2 plus 1/2 cosine 4x. I'll just combine this 1/2 here with the 1 and make it a 3/2. And so this right here, this will be our formula for cosine to the fourth x. And now I think we have all the formulas we need over to the right. And all I want to do is, working on this integral, let's expand out 1 minus cosine x to the fifth. You can do this with binomial theorem. We can look at it. I'll just call it 1 minus a for the moment. If we expand this out, let's see what we get. And now that we have this expanded, I just want to look at each term individually. And of course, for each of them, we're multiplying by cosine 5x. Our a value is cosine x. So starting with 1, if we multiply 1 times cosine 5x, we have cosine 5x. But when we put this back into the integral, this is just going to be 0 using this first formula. It's going to integrate the sign. So this 1 is going away. And then for this minus 5a, I don't even really care about constants, because if it's going to be 0, it's going to zero out everything. So for a, we're looking at cosine x times cosine 5x. But this here, when you put it back in the integral, this is going to meet this second formula. So this is also going to be 0 when you integrate it. So this is going away. Okay, next looking at a squared, that's going to be cosine squared of x, but we have this formula here for that. Again, I'm just ignoring the constants in front. As long as it's 0, we don't care about what constants we're multiplying it by. So then writing out cosine squared this way, again, we're multiplying by cosine 5x on this. Distribute this out. Again, this one meets the first formula, just one cosine, so that's going to 0. This is 2 cosines with different angles, meets the second formula, that's going to 0. 10a squared, also going to 0. At this point, you might think that the answer to the integral has to be 0 because pretty much everything is going away, but the one thing we have to look out for is this case here. As long as a is not equal to b, everything's going to be 0, but the case where the angles match, then we have a different formula. Let's look at that really quick. I should have probably put it down originally, but if we have the same angle, we can call both of them a. So if we have cosine squared ax, then what you can do on this is basically use this formula, inputting ax on it, and it's going to be really similar. You're going to have 1/2 this integral from 0 to n pi, and then this stuff here. But then what you'll notice is even when the angles are the same and you have cosine squared, if you break this into two integrals, this second one meets the first formula. So this thing, you integrate it to sine again, this piece is still going to 0. So what you're left with actually in this formula is now you're just integrating 1. So you integrate this, you just get 1/2 x from 0 to n pi. This is 0, so you plug it in and you get n pi over 2. So let's keep this, because if we eventually get something where the angles are the same, it's just going to be n pi over 2 times whatever constants might be up front. So now continuing on to our a cubed case, that's going to be cosine cubed. So if we have cosine cubed x, we'll use this formula right here. Again, ignore constants, multiply in the cosine 5x, distribute everything out, and let's see what you have. If you put it back into the integral, of course you could separate this into two integrals, but both of them would be in this second form, multiplying cosines. So both of these are going to be going to 0. And again, nothing going on there. Next, moving on to a to the 4th, we have our formula here for cosine to the 4th x. Again, get rid of constant values, multiply in cosine 5x. And then I'll just multiply in the cosine 5x, but I think just looking at it, you can probably see what's happening here. You don't really need to distribute in, but I'm just doing it to show you what's happening. Then if you take this whole thing that we have here and throw it back in the integral, this first one meets case 1. It's just integrating a cosine to sine, so this one's going to 0. Putting these in separate integrals, they both meet case 2. And so that's going to 0. They're all going to 0. This thing is going to 0. So after zeroing everything out, all we have left is minus a to the 5th, which is just minus cosine x to the 5th times cosine 5x. Let's put this back in the integral and see if we can finish it off. Okay, now what we have left is quite a bit simpler, but I still need to reduce the power on cosine to the 5th because we don't really have a good way to work with these things. And I don't really have a formula yet for cosine to the 5th x. So what I can do is, for cosine to the 5th, in order to get it into something we're more familiar with, I'll write this as cosine to the 4th x times cosine x. That way for cosine x times cosine 5x, I can use this formula right here. And then cosine to the 4th x, we'll use this formula, multiplying this all together. It's going to be all this stuff here. So when I multiply these together and put it back in the integral, what's going to happen is, here the constants I can bring out front, 1/2 times 1/4 is 1/8, and we still have this minus sign here. And then what you'll notice is we don't really need to distribute all this stuff out because, like, first of all, 3/2 is a constant. So then when you multiply 3/2 times this, you're just going to get single cosine integrals. That's going to meet this first case, and those are all going to be 0. So that's going away. Multiplying cosine 2x into this also doesn't help us because it's got a different angle. 2x doesn't match 4x or 6x. So those are all going to meet the second case. It'd be different angles. Those are all going to 0. So like everything's going to 0 except what you'll notice is this last one, we have cosine 4x. And so the angle actually does match this here. So I will distribute this back in here. I'll cross this one off, but this is again going to be 0 because we've got different angles. So when we multiply this one times this one, we get just 1/2 cosine squared of 4x dx. Well, I can take this 1/2 and multiply it by 1/8 and get 1/16 here. Clean up all this mess over here that we don't need. And now that we have it finally down to just one term, notice this is in the same form as this here. We could do it out with this formula, but we really already did it, so we'll just use the formula. Again, now the a value on this is 4, but notice there's no dependency on the a because the solution just has the n. So what we want is the n value, which is 2. So putting this together, we're going to have minus 1/16 n pi, so it's going to be 2 pi over 2. 2's cancel out, so for my final solution, we just get minus pi over 16, and that's it. So this is kind of a weird one where it's actually really straightforward and easy. It's just really tedious. So I know there's a time limit. I don't remember if this one was 2 minutes or 4 minutes. But if you multiplied it out and had to reduce all the cosine angles, I don't really think you could do it in 4 minutes. You needed to use something, maybe not this exactly, but something where you just could quickly identify all the 0 integrals, get them out of the way, and get basically to this point in like a few seconds. And basically, if you could get to like this point in 30 seconds or a minute or whatever, then I think you're probably okay, because then this is pretty straightforward stuff at the end. Okay, that's it for today. Thanks everyone for watching. Have a good day.